Okay, so as I had mentioned in the previous week, there's no class on Wednesday. The next class is going to be on Friday. And if anybody needs to talk to me for office hours or something, we can meet on Friday after the class. Okay, so I'll keep some time free after the class. So in case if any of you have questions on the assignment or anything, we can talk right after the class. And then they're like, okay, so we were talking about conjugate direction method in the previous lecture. Um, right, so in that particular, so we have been talking about gradient descent method. So conjugate direction is related to gradient descent because we are using the gradient in order to compute the conjugate direction. Today we want to talk about quasi-Newton method. And the idea of quasi-Newton method is very interesting. It basically says that since we are computing the gradient, and what is the second derivative? Second derivative is gradient of gradient, right? So if we are computing the gradient at multiple time steps, like at every point of time we are computing a gradient, why don't we just take the gradient of gradient and assume that that is the second derivative? Okay, so that's the idea. So let's think about it. I have computed gradient of fx naught, gradient of fx1, fxk, and what I know is gradient of fxk plus 1 minus gradient of fxk equals to, well, not equal to, let me make it an approximation. Do we all agree with this? This is just Taylor series, okay? But I'm just taking the first order Taylor series approximation of the gradient. And what do we know from our experience? So step size is small. So this term is going to be small. So if this term is small, then this is a very good approximation for the first derivative. So this is roughly what we have in terms of the approximation. So I'm going to give it a name. So I'm going to call this QK. I'm going to call this PK, and this is my dk plus 1 inverse. Remember that my dk plus 1 has to be positive definite, and this is given by second derivative inverse. Yes. Is that 9K? QK. Q. I'm so sorry. Okay, so this is QK, not 9K. All right, so I'm going to push you back to 1970. So you are a graduate student in 1970, roaming around in the hallway. Somebody asks you this question. I want to come up with a dk that satisfies this expression, or dk plus 1 that satisfies this expression. What would your gut feeling be? How would you want to approach this problem? Any thoughts? So you've computed gradient of fx naught, you have gone to gradient of fx1, you have done this computation, you have gone to gradient of fx2. Somebody tells you, hey, you know what? gradient of gradient is the second derivative. So I want to come up with an approximation to the second derivative, so I can exploit this sequence of qk's and pk's that I have generated so far. I can exploit it to compute some approximation of dk plus 1. So I have some d naught. Let's say it's an identity matrix. I want to pick the simplest matrix possible. So I have d naught, which is identity. I want to come up with d1 based on this information of q0 and p0, or p1 and q1, whatever that index is going to be. What would you do? How would you approach this problem? Okay, so it's somewhat difficult to figure out what should the update scheme for dk look like, but here is a simple insight. Let's try to say that if I'm going from dk to dk plus 1, I'm going to do maybe a rank 1 symmetric matrix update, or a rank 2 symmetric matrix update, or maybe a rank 3 symmetric matrix update. So you all know symmetric matrices, right? We have all studied that. What's a rank 1 symmetric matrix? I want it to be symmetric, right? Remember, positive definite matrices are supposed to be symmetric. So if I'm starting with a positive definite matrix, I want to make sure that every point of time I get a positive definite matrix. So what's a rank 1 symmetric matrix? It can be given by AK, ZK, ZK transpose. So AK is a scalar, ZK is a vector. What does ZK, ZK transpose look like? So let's pick a ZK, just a 2 cross 2 ZK. So 2, 1, 2, 1. This is my ZK, ZK transpose. What is this matrix? It's 4, 2, 2, 1. Is it a symmetric matrix? Right? It's a symmetric matrix. I'm just multiplying it by a scalar. So multiplying a symmetric matrix by a scalar gives you a symmetric matrix. So that's a rank 1 matrix. It's a rank 1 matrix because the rank of this particular matrix is 1. What's a rank 2 matrix? It's AK1, ZK1, ZK1 transpose, AK2, ZK2, ZK2 transpose. Again, AKs are scalars and ZKs are vectors, and it gives you a rank 2 matrix as long as ZK plus 1 and ZK plus 2 are linearly independent. So that's a rank 2 matrix. Okay, so if I want to add a rank 1 matrix to dk, I have to figure out an AK and ZK so that I can compute dk plus 1. If I want to add a rank 2 matrix to dk, then I have to figure out 4 parameters, 2 scalars and 2 vectors. And the vectors have to be linearly independent. What should we do? So I start with a symmetric positive definite matrix. I want to add another symmetric matrix to it. So I know that the new matrix is going to be symmetric. I hope, I'll pray to God that the new matrix is also positive definite. And hopefully that will help me compute dk plus 1 that satisfies this particular expression. Okay. What's the simplest update? So let's say we don't want to complicate our life. We'll pick a rank 1 matrix, which is this. So I want my dk plus 1 to be dk plus ak zk transpose. And what else do I want? I want dk plus 1 qk to be equal to pk. Not equal, but approximately equal to pk. So that's the two requirements that we have on dk plus 1. Does it sound reasonable for 1970s, right? So I don't have too much computing power. The best computer I have is a microcontroller. I need to be able to execute an optimization problem on that microcontroller. Maybe I don't even have a microcontroller. I don't know. Maybe mainframe was the big thing at that point of time. I've not lived in 1970s, so I don't know, but I'm sure there are faculty at OSU who lived in 1970s and they can advise better. But let's go back to 1970s. So I want to implement Newton's method. I cannot compute the second derivative inverse. So I need to come up with something that is simpler than computing second derivative inverse. I want to enjoy the Newton's method convergence, but I don't have the computational power. I'm running these optimization algorithms on simple machines. So somebody suggested, I was walking in the corridor and somebody suggested, why don't we just do a rank 1 update, symmetric matrix update to dk? As long as it satisfies, maybe I'm good. Okay, let's hope, let's pray to the God that we are good with this rank 1 update. So let's try to understand this. I'm going to define Rk to be Pk minus dk qk. This is Q, this is A, yeah, qk. And my goal is to find ak in R or gk in Rn such that dk plus 1 is positive definite. Okay, so what should I do? I have dk plus ak zk transpose times qk is equal to pk. That's this term. So remember, this is an approximation here, but I'm going to make it equality here. Okay, because I just want to get some approximation of dk plus 1. So let's just make it equality. Okay. So I can rearrange the terms and I can write, let me write it here. So I have ak zk transpose qk is equal to Rk. Okay, this will be our guiding light for quite some time. So this is the identity I get, which means that my zk can be written as ak zk transpose qk times Rk. So remember, this is a scalar, this is a scalar. I'm dividing 1 by a scalar quantity, so that's a scalar. I'm multiplying it by a vector rk. So rk is a vector. This is an Rn. So what is AK, ZK, ZK transpose? So I get the value of ZK from here. I get some expression. I want to multiply it by AK, ZK, ZK transpose. What do I get? I get RK, RK transpose over AK, ZK transpose QK square. This will be our second important equation. There is a problem here. The problem is that I wanted to find this matrix, this rank 1 update term, but it turns out that this rank 1 update term actually depends on both AK and ZK on this side. So RK is something that I can compute. This is something that I know. I can compute it exactly, not a problem. But the denominator is something that I cannot compute. So how do I compute the denominator using quantities that I already know? Okay, so I see this AK ZK transpose QK is equal to RK, but there is this term ZK, this vector ZK that's sitting here. This is a scalar, this is a scalar. There is this vector sitting here, and I know that this equation is equal to RK, and I need to find the denominator. Does something ring a bell? Can we compute the denominator using this expression? So what happens if I multiply this side and this side by QK? So I get from this expression AK ZK transpose QK ZK transpose QK equals to RK transpose QK. I know RK, I know QK, and this is the rank 1 update term. This is RK transpose divided by some scalar. Now what I have done is, this scalar is unknown, right? Because there are quantities within the scalar that I don't know about. But what I was able to do is massage the equation enough so that I can compute the scalar as a function of stuff I already know about. I know QK and I know RK. I can compute it. So now I'm going to substitute this in the denominator. So remember AK ZK transpose QK square, that's exactly this term. So what I have is dk plus 1 equals dk plus 1 over RK transpose QK RK RK transpose. So this is the rank 1 update that I get. If I use this rank 1 update, I guarantee that this will be met with equality. Question? Yes.
Does this mean that for D0 you must compute the exact D0?
D0 has to be, it can be identity matrix or something.
Oh,
So you start with some very bad approximation of the second derivative, and slowly you want to converge to a good approximation of the second derivative.
oh,
As long as at every point of time you are positive definite.
oh,
The only requirement on dk, if you recall, is that dk plus 1, dk's have to be positive definite. That's the only requirement, right? So as long as I can ensure that at every point of time I have a positive definite matrix, at least the gradient descent part is working fine, and hopefully we'll get to second derivative inverse at some point of time in the limit, right? So if this condition is satisfied at all times, then it means that you are close to being second derivative inverse. What is the problem? Why would someone say, so let's go back to 1970, you did this thing over a weekend, you came up with this expression. Why would someone say that this is a very bad algorithm? Why is this a very bad algorithm? Yes.
Where it goes like the 1 million and the 1 million.
We are not even at 1 million yet, but this is a bad algorithm even at time k equals to 0 or 1 or 2 or 3 or 4. Why is it a bad algorithm? So I came up with a rank 1 update, and remember my requirement is I want to find ak and zk such that this is positive definite. What would make this a non-positive definite matrix? So it might have a bunch of positive eigenvalues, but it could have a negative eigenvalue. Why would that happen? It would happen because of this denominator. So if the denominator was positive, life was good. This would be a positive definite matrix because this is a positive semi-definite matrix, and I started with a positive definite matrix. So I'm adding a positive semi-definite to a positive definite matrix, I get a positive definite matrix. However, there is no guarantee that this particular term will be positive. Okay, it could be negative. And if it is negative, now you have a positive definite matrix and you are adding a negative semi-definite matrix. I don't really know if dk plus 1 is going to be positive definite. Okay, so that's the problem with this particular algorithm, which is even if I start with a positive definite matrix, I'm adding potentially a negative semi-definite matrix depending on the sign of Rk transpose Qk. Consequently, after a certain period of time, I'm no longer assured that dk plus 1 is going to be a positive definite matrix. So this condition is not satisfied by this rank 1 update. That's a big disappointment. We need to come up with a new idea. So guess what's the new idea? The rank 1 update did not work. Let's pick a rank 2 update. Okay. Now there are two different philosophies for rank 2 update. Philosophy number 1 is known as DFP algorithm. Which says that dk plus 1 equals to dk plus rank 2 matrix. And the philosophy number 2 is BFGS algorithm, where the idea is dk plus 1 inverse equals to dk inverse plus rank 2 matrix. So either you compute the second derivative and add the second, add a rank 2 matrix to the second derivative, or you pick the second derivative inverse and add a rank 2 matrix to the second derivative inverse. So those are the two different philosophies. And of course, this is 1970s, right? So a lot of people have worked on these algorithms since then. And the book says, the nonlinear programming book that we are referring to, dk plus 1 equals to dk plus rank 3 matrix. Which seems to be the at two extremes. So this is a parameterized algorithm. So at two extremes, you recover DFP and BFGS algorithm. But at the same time, you have some free parameters to pick in order to make sure that your algorithm converges. So what is that rank 3 matrix? So I'm going to introduce a few terms. So I'm going to define what the rank 3 matrix update is. So I'm to define a few vectors. So Vk is Pk divided by Pk transpose Qk minus and now dk plus 1 Pk transpose Okay, so this is the expression. So what are we doing here? We have, so tau k is qk transpose dk qk. Is this a positive number or a negative number? Is this positive or negative? It's a positive because dk is a positive definite matrix, right? So I'm pre-multiplying it by the same vector. So tau k is a positive number. Ck is something between 0 and 1. So naturally it could be 0. So it's a non-negative value for sure. Vk is just a vector. So this is just a vector in Rn. So this is a positive semi-definite matrix because I have a positive number multiplied by a symmetric matrix, rank 1 matrix. So this is a positive semi-definite matrix. What about Pk transpose Qk? Is this positive or negative? So what was Pk and Qk? Pk was the difference of xk, and Qk was difference of the gradient. What do you think the value of this scalar is? Let's think about it. So xk plus 1 minus xk transpose gradient fxk minus 1 gradient fxk. Is this positive or negative? Okay, let's try to do some more approximation. Xk plus 1 minus xk transpose second derivative is it positive or negative? What do you think? Positive, right? So we expect that the second derivative is positive. So this is positive. So this term is positive. So we have a positive semi-definite matrix here. What about this term? So tau k is negative. I have some vector transpose form here, but with a negative sign. So rank 3 update again leads to positive definite plus positive semi-definite plus positive semi-definite plus negative semi-definite matrix. But what can I say about dk plus 1? So it turns out that there is a theorem in the book which says my dk is positive definite and alpha k is picked such that gradient fxk plus 1 transpose dk is greater than gradient fxk transpose dk. Then dk plus 1 is positive definite. So by picking an appropriate step size, I can ensure that my dk plus 1 is also a positive definite matrix. Okay? So I'm computing pk's and qk's at every point of time. I am deriving, I'm updating this matrix second derivative inverse estimate at every point of time using this update equation. By picking an appropriate alpha k, I'm guaranteed to have a positive definite dk plus 1. And the benefit of this algorithm is that we are trying to imitate Newton's method, and therefore we get the speed up that is associated with Newton's method without necessarily computing second derivative inverse. So remember, dk is supposed to be second derivative inverse. Everything here is just matrix multiplication. I'm not converting any matrix inverse here. So one thing that we know from our experience so far, matrix multiplication is good, matrix inverse is bad, okay, for execution of an algorithm, especially when you are dealing with large matrices or when you are dealing with small devices, like the computational device is not powerful enough. So in those situations, you want to pick DFP method. So you want fast convergence. You don't want to have the overhead of matrix inverse. You pick quasi-Newton method. For C equals to 0, if this C is equal to 0, then it is DFP method. If C is equal to 1, then it's a BFGS method. Let me write it here. CK equals to 0 is DFP. CK is equal to 1 is BFGS method. Okay, so the philosophies are written here for the two methods, and this is what the this rank 3 update, this is what it basically means. By tuning this parameter CK, you can go between one method or the other. Any question? Yes.
Is QK equal to alpha k?
So this is my QK. Not quite, right? So DK,
Yeah.
XK plus 1 equals XK plus alpha K DK gradient fxk. Okay, and this is my dk. Okay. Any other question? Okay. So that's concludes our quasi-Newton method. There is connection. I mean, if you're interested in the book, quasi-Newton method for a quadratic optimization problem is equivalent to conjugate direction method. So there is connection between what we learned in the previous class and what we are doing here. Yeah.
I mean PK, the difference of x.
Yeah, that is definitely.
Oh,
Pk is alpha k times dk. Yeah. Any questions so far? No? Okay. Wonderful. So let's try to motivate the next method that I wanted to talk about. So one thing we recognize from the direction here, like what you see here, is that the update term for decays, no, actually go back even one step before that. So we want to speed up the algorithm by taking the nonlinear transformation of everything that we have computed so far. Okay, so we have computed a whole bunch of vectors, we have stored it in the memory, and we are taking a nonlinear transformation of all these vectors that I have computed in order to compute my next descent direction. Okay, one might ask, again going back to late 1970s, one might ask that what if we just want to stick to linear combination? We don't want to make this sophisticated nonlinear combination, and instead I want to pick something that is simple and straightforward. Okay, so what is the idea? So I'm going to talk about momentum methods. So what is the idea? So I have computed gradient fx naught, gradient fxk. And what are we doing so far? We are saying that I'm computing all this stuff. I had actually stored it in the memory also. But then what I'm going to do is forget everything that I've computed in the past and just use the gradient that I've computed right now in order to do the descent. Okay, then somebody said, guess what? You can do a lot of nonlinear transformation of whatever you have computed so far You can compute this matrix dk based on the nonlinear transformation multiplied by the current gradient. You get quasi-Newton's method. Now you might say this is too complicated. I have to compute some matrices. It's so many vectors that needs to be computed. I don't want all that. I want something very simple. What I want is, I want my dk to be summation. I've already used alpha. I need to use a scalar. What's a good scalar? Beta. Beta ki gradient fxi. I goes from 0 to k. Beta is a scalar. I want to pick the descent direction of this form. I want to pick a descent direction that is linear combination of all the gradients that I've computed so far. So again, I'm going back to so this is, all of this stuff is 1975, 6, 7, something like that. I'm moving to 1979 or so for this method. Okay, so the question is, how do we compute algorithms that are of this type? Well, I'll give you two algorithms that tends to imitate that. I have zk plus 1 equals to I'm trying to remember. Okay. So I was hoping to come to talk about this in the next class, but because we have some time, I'm trying to recall from my memory what the algorithm was. So give me some time, I'll write it down. So I have zk equals to xk minus no, not xk. I'm not using xk here. You know what, I'm thinking that maybe I need to look at my notes. I don't have my notes here for this algorithm. So I'm going to end the class here. We'll continue with this discussion in the next class. I'm not able to recall what the algorithm was, but there is some term here that I'm forgetting, whether it's yk minus 1 or zk minus 1. So instead of giving you the wrong algorithm, let's cover this in the next class. So that is momentum method. We'll continue with the momentum method in the next class, and then we'll talk about optimization over convex sets. Okay. So thank you so much, and we'll meet next Monday. On Friday.